And so good afternoon, everyone, and welcome to our webinar, How to Secure ICS and SCADA Systems, Strategies That Work. This webinar is presented by the Research SOC, the National Science Foundation Security Operations Center for Research. You can visit us at researchsoc.iu.edu. I'm your host, Todd Stone. Today's moderator is Josh Drake. In a moment, Josh will introduce our two special guests, but first, let's take care of the housekeeping details. For this webinar, all attendees are on mute. Now you can ask your questions using the Q&A feature at the Zoom control panel on the bottom of your screen. If time permits, we will address those questions during the Q&A period at the end. And if we don't have time to address all those questions, I encourage you to ask them in our Research SOC community of practice on askcyberinfrastructure.org. I'll have a link to that at the end of the webinar. This webinar is being recorded, and the recording and the slides will also be available on the Research SOC website. With that, let's bring on our moderator. Josh, please take it away.
Thanks, Todd. It's good to see everyone here today. Today we're going to be discussing the ICS landscape with our two presenters. My name is Josh Drake, and I am a senior security analyst at CACR, the Center for Applied Cybersecurity Research at Indiana University. I have 15 years background in systems and networking, and the last 5 or 6 of those was spent at municipal government and public utilities, where I was responsible for some ICS and SCADA systems there. Since about 2007, the focus on industrial control systems and cybersecurity has greatly increased due to the accelerated frequency and severity of malicious attacks on ICS infrastructure. Back in 2007, we had the Aurora attack at Idaho National Labs, which was a demonstration that malicious code could be used to cause physical damage, which they demonstrated by blowing up a diesel generator. More famously, in 2010, we saw Stuxnet was used to destroy hundreds to thousands of centrifuges at an Iranian nuclear enrichment facility. More recently, we've had incidents in Ukraine where crash override was used to take down power generation. And even in 2017, Triton was able to disable safety systems at oil refineries in Saudi Arabia. So the frequency and severity of these incidents continues to increase. For the last decade, the number of alerts released by ICS CERT authorities has increased year over year. In the first half of 2018, Kaspersky's ICS CERT estimated that up to 40% of all ICS attached computers were being subjected to some sort of attack. As our devices become more connected to the internet and start to share more common architecture with traditional PC architecture, as well as our network topologies continue increasing in complexity, we expect this trend to continue. The days where we could just air gap an ICS system and keep our heads down and hope no one notices are gone. These are now targets for attackers. I am guessing that a lot of you here today, like me, have come from the information side of the IT versus information versus operational technologies. And while similar, there are substantial key differences that make securing ICS environments more challenging. The priorities of industrial control systems are different from those in traditional IT. We want to place a higher emphasis on the integrity and the availability of these systems, and that may mean that it is more difficult or even undesirable to patch them due to issues of remote access or especially systems that require validation if they are changed. Additionally, we have systems that are designed for much longer lifespans than what we traditionally see in the information technology world. I'd be very lucky to get a server to run for 7 or 8 years, but in the ICS environment, 20 years and more is quite normal. And finally, we have just different types of language, different terminologies, different security controls, and methods that we're used to in the IT world don't necessarily apply when talking about operational technologies. These sort of environments require careful planning and critical thinking to be able to secure them effectively and affordably. Thankfully, today we have with us two experts in the field who are going to walk us through some strategies for dealing with ICS incidents. Security, and let me just pass control over in a second here. Our first presenter is Dr. Stefan Lüders. He received his PhD from the Swiss Federal Institute of Technology and joined the European Organization for Particle Physics, better known as CERN, in 2002. Since 2009, he has headed the CERN Computer Security Incident Response Team as CERN's Computer Security Officer, where his role is to coordinate all aspects of CERN's computer security, including office computing security, computer center security, grid computing security, and control systems. All this while taking into account CERN's operational needs. Dr. Lüders has given presentations on computer security and control systems, cybersecurity for companies, governments, and international bodies, and he has also published several articles. I've lost my screen. Just a moment here, I need to...
Stephen has control.
Okay. All right, go ahead. Thank you.
Oops.
Stephen, if you can go ahead and share your screen.
Oh, he's using your screen, isn't he?
It's very nice. Can't find my slides.
Can you go to slide 9?
Good. While you're trying to set up my slides, I wonder because it was working very, very nicely yesterday. So thank you very much, Josh. So I'm Stefan from CERN. In principle, I would like to talk about why control system cybersecurity sucks. I'm working in this field since more than 18 years, starting with control systems, having done control systems for big accelerator installations, particle accelerators like run those at CERN. For large-scale physics experiments. I've seen control system for astronomy telescopes, for telescope arrays. And what I would like to discuss this more or less, what are the problems we are running into? So can you find my slides? Gentlemen.
Is that...
We're having a little technical difficulties. We'll get there.
Nicely. Good. Just to give you an idea about control systems, accelerators, and experiments. If you have never seen one of those accelerators, the biggest one is the beast we're running here at CERN. It's 27 kilometers long. It's run by industrial control systems, partially bought from industry. It's run partially by industrial control systems developed by our community. Here we are. Let's see if I can control that part. Good. And those control systems are quite huge. So I would like to talk a little bit more why control system cybersecurity sucks. And this starts with something very, very basic about devices which we're buying out of the market. So you can see here an RS-232 port converter to TCP/IP, which you just buy out of the shelf, completely unprotected, no security means nothing, even if there's a security button. Here is a control system which we're using for our conference rooms. Usually we get in conference rooms lots of buttons where you can enable remote laptop, HDMI, VGA, turn on and off the projector. You can do this remotely via web interface. Guess what? Not protected. So I hope nobody's spoiling this presentation now. Printers like this one, you can change the text once you have access to the network. Internet of Stupid Things, unprotected. Here's a PLC which you're running into thousands. It's a PLC from a well-known European brand, but this doesn't matter. Those PLCs, programmatic logic controllers, come also without any security protections. You can see it here. You can define a password, but it's talking about HTTP access rights, and HTTP is going via clear text over the wire, which means you would like to have HTTPS, but that is a feature you have to pay extra. Going further, this is a power supply which we're using at CERN. If you look a bit closer, you can see 3 Ethernet ports. If you do a denial of service attack against one of those ports, meaning sending 70 seconds of garbage into this power supply, the power supply is dead. It still will give you the 12 volts, the plus minus 6 volts, the plus minus 3 volts, but the control is gone, which means you have to go then pull the power plug. Not a problem if you have got only one in the office or in your lab. We are running thousands distributed over the whole site, which means that I need to have at least a couple of dozen students just to run around to reset those power supplies. Similar for this beast here, this is a very small dosimeter reader. You put your dosimeter into the small little slot, which you can see on the left bottom side. And if you look a bit deeper, you see the gray Ethernet cable getting out. Again, here, if you dump it with garbage, it will just core dump. Completely crash. You can extract the core dump, and if you look in the core dump, what you find is the telnet password in clear text. So those devices can be also hacked. We tested lots of other devices. Here's an oscilloscope running Windows. You see here the blue screen of death. And we tested those devices in 2007 and figured out that something like 1/3 of the devices are more or less either crashing or they're failing. Failing means that the web server, the FTP server, the telnet server, or whatever else it's running is not functioning properly anymore. More recent tests, just done last year, we tested 900 different devices, and what you can see from this pie chart here is 25% of the devices have some vulnerabilities. They are not secured. So this is where it's starting, where control system cybersecurity sucks, because there is no incentive for the vendors of devices for the Internet of Stupid Things to make those stupid things secure. Go home tonight, look at your web camera, look at your fridge, look at your coffee machine, look at everything what is Ethernet connected, and I bet with you that it will be not secure. So how can we create incentive in making the vendors to produce us secure devices? This is what me and my community is struggling with. We would like to see manufacturers liable. There are just 2 products worldwide where the end user like me is assuming the responsibility and the risks of the product we're buying. Software and hardware is one, where if I'm buying an operating system from Red Hat or from SUSE or from Debian or from Microsoft, I have to patch it, I have to guarantee the security. I can't go back to those ones and say, look here, it's insecure, I would like to have my money back. Doesn't work. What is the second project, object I can buy on the market? You get an idea? Drugs. If you buy drugs, you can't get your money back if it's not working. So this is already odd, isn't it? So we need to have legal requirements, maybe for bug bounty programs for those manufacturers. The European Union has tried to something which is called the Segregation framework for control system devices. Not sure if this is flying. The US has been earlier. The Department of Homeland Security, the Idaho National Lab, developed something like a security procurement language for control systems, which means that you copy paste out the paragraph for your tender, and once you got this for your tender, you can put it in and you can give it to the to your supplier of your software, your hardware, and they have to fulfill it. We tried 2009, we tried 2010. The result was most of the tenders were not fulfilled because every vendor came back to us and said, look here, we can give you that bit and that bit, but the security bit we can't. There's no market demand. If you want to have this one, not with us. So this is why cybersecurity sucks. Oops, and here are other devices. Those are devices which are now new on the network, again PLCs, but they're devices like Raspberry Pis, Arduinos, systems on the chip, Xilinxes, all those embedded devices which my community, the physicists, are using more because they're very easily to generate, very easy to program, and they're very, very flexible to do control systems. But how do I patch them? How do I keep a Raspberry Pi up to date? It's much, much easier with a Linux system, but Raspberry Pi is another beast. And we're not talking about the system of a system on a chip where it's even more complicated. Just patching an Altera chip or Xilinx chip, this is not easy. So what we're doing, like everybody else, we're trying to have a prompt patching mechanism, like my iPhone is doing a prompt patching, but we are far, far, far away from this, because you have to respect that you have downtime, you're creating downtimes when you're patching, you have to have technical stops to do all those ones. Think again, you do not want to stop your industrial fabric to do the patching. And then we have to talk about security measures, which are provided by those vendors, but they ask you for double the fee. So they have fantasy pricing once you're asking for security features. So this is why control system cybersecurity sucks. Looking deeper, this is a typical device we're using also for control system. This is a very small PC here. It's an Intel Nuke. Nice, very, very compact, very, very powerful. First problem is it comes with 2 USB ports. This is already problematic because if you don't have proper physical protection, somebody can just put in a detected USB stick and take over your device. Fine, we got this under control. But the next thing what's coming is those devices come now with embedded wireless access points, with embedded wireless, everything on the chip. You cannot put glue into the USB port. You can't put glue on the motherboard. You can't get rid of the chips. So now what do? You are buying those devices, but if you order them without any wireless connectivity, you pay double fee. So how can I deal with this one? Wireless access points all over the place in all my caverns. And in the future, we got even the long-range wireless access networks, which are even another beast, because there the signal is even much fainter and it's more or less without any security. So this is why wireless on the plant floor completely sucks. This is how my network is looking like. Every small little black bar is a control system device. You can see more or less that we got different domains. The green domain is for monitoring. There's the blue domain for power controls, the orange domain for cooling ventilation, and all the other control systems for our actuator. The actuator has something like 128 different control systems. The smaller ones have a couple of PLCs. The bigger ones, we're talking about a couple of hundreds, if not thousands of PLCs, HMIs, user interfaces, and SCADA servers. So looking at this one from the book, you would like to have network cells, which you can protect, and then you interconnect the network cells. So your control system hierarchy is something like a tree. I don't see a tree here. All the systems need to talk to each other. The power supplies need to know what the status of the beam is. The cooling ventilation needs to know what the status of the power supplies is, and everything is interconnected. So network cells can't do. Everything is a very, very big network cell. Very, very difficult to generate the security inside. So and even controlling the interdependencies between the systems is already a challenge. And last but not least, if I would like to pull in a firewall, my firewall needs to be highly redundant, highly available. So if the firewall is going down on one side, I got the backup, which is just kicking in. But if you look at the firewall with doing stateful filtering, it's memorizing your sessions. If one is going down, everything in the memory is going down too. So making firewall segregation, while you can do this, it's also becoming very, very difficult. And this is another reason why control system cybersecurity sucks. We're even forced in the future to use external license servers. Remember this Intel Nuke? This Intel Nuke is running Windows for a certain control system. Yes, I know you shouldn't run Windows, but this is what the vendors just can. They can run Windows. They don't come with a Linux platform. So now, for enabling my Windows installation, I might be forced in the future by Microsoft to have a remote connection to Redmond somewhere in California to authorize my installation at every startup. If I want to use Excel for some internal processing for mathematics on certain values, I might need to license the software and having their license server in Redmond somehow giving me the authorization to use the software. I don't want to connect my control system directly to the internet, having them talking to Microsoft or to Oracle or to GitHub or to all the others. So it's getting more and more complicated, and this is why control system cybersecurity sucks. This is my computer center, 1 out of 7. This one has 12,000 enclosures, meaning 12,000 servers, something like 100,000 cores, 100,000 hard disks. And this computer center is used also for running our control systems. They are giving all the databases, they're giving all the infrastructure, all the industrial application. But if you look how to manage a computer center today, the computer center is starting with a small bare metal. This is your pizza box PC, which you buy from Dell, Supermicro, HP or others. So it has one connection already to the BIOS, which is the IPMI and BMC, first connection. Then you have the hypervisor, because you virtualize everything. So your hypervisor has a connection and all the virtualization on top of that. And then people come to the clever idea having Docker containers or Kubernetes. And even our control system experts are now running all their software into containers like Docker or like Kubernetes. So now you get a layer, a huge stack of complexity, and there it's very, very difficult to generate all the security for those parts. And I would like to generate it only once. So there's all the provisioning of the virtual machines, there's monitoring of the virtual machines, and how do I split now those services? Because this computer center is also used for finance applications, for HR applications, for compute, for physics computing, and even for web servers. So of course I can now scale the computer center and divide it into three. That is a very, very clever idea. So I have three computer centers. One is for the control systems, one is for the standard IT, and one is for the internet. But hold on, all of them need to have single sign-on, an Active Directory, LDAP. They need to have NTP. They might have the same provisioning system. So all those systems need to talk to each other, which means that my three separate computer centers are moving together again, because it doesn't make sense having everything triplicated. It will just triplicate the cost. And for example, for single sign-on's idea is you just have one account, one password. So you need to somehow funnel this between the three computer centers. And the same for provisioning. And if you provide central patching for Windows and for Linux, you just want to have this once and once for central. So question is, how do you have segregation for different purposes, internet, IT, and control system, while you would like to have, just because of cost, a centralization? So control system, cybersecurity, and even security in general for computer center sucks. And if you do programming, which some of you might do, programming is even more complicated. Nowadays, the idea of the internet is you go to Google and you look for your code and you implement your code into your software and you download just packages. But how do you control those packages that the packages are sober and clean? Here's an example of a NPM, where typo squatting mistake was undetected for 2 weeks. And luckily for those ones who downloaded this one during the 2 weeks and got now some malicious code. Or here, the SSH decorator package, which comes with a backdoor, which is marked by the arrows. So if you have used this, copy-pasted this code, now you have a backdoor in your control system, or everywhere else where you're using this. Here's last example, REST client published with malicious backdoor. Hooray. So the whole idea is, we are in IT, in software, we are profiting from all the others. This is the idea of software, reusing software, not reinventing the wheel. But if we pull in external software libraries, like via PyPy or via NPM, how do I make sure that this code is clean? Of course, I can analyze the code for 12 lines. For 100 lines, I can run code checkers on top of them, but they will never get everything. So this is the next problem I'm facing into. So how do I make sure that blunder, bugs, and vulnerabilities are detected early enough? There are tools for this one, but none of them are catching everything, and you have to centralize this. I would be interested how you guys are doing this. This is a hard nut for me. I give it 2 bombs. Still something I think I can control. Here you can see a real accelerator. You get on the left, top left, you got this test stand, but the other 3 pictures are showing our tunnel, 27 kilometers long. This is a one-time prototype. This world can just afford one. The large-scale physics experiments here run at CERN, which are the size of cathedrals. They are just existing once. There are other accelerators, small accelerators, all around the world, also in the US, but also those are dedicated machines for one purpose. If you look at telescopes, telescope arrays, they are just existing once in an array, which means that they are all one-time prototypes. You just can't develop them, then you seal them and you let them run. This is a permanent development on the real systems. And this is a permanent development for making the system better. New changes, new features. So you just can't disconnect this from your office computing network or even from the internet, because the experts need to have remote access to the system. So how do you split development, initial testing, final testing, the rollout, and the operations from each other? Of course, I can have test stands, but some of the parts just can be tested when they're interacting with the overall. The actuators here at CERN, they more or less interact with everything. The beams interacting with the beam pipe, which is just a tube. They interact with the magnets, which are guiding the beams. They're interacting with the lake, with the water level in the Lake Geneva, which is around the corner. They even interact with the fast-speed train coming from Paris, because this train is just a big magnetic field, electromagnetic field, which is interacting with our beam, and you have to correct this for. So having a test stand for this one, very complicated. Control system cybersecurity purely sucks. Authentication authorization, this is the webcam. Default username is admin and password is 1234. If the devices of the internet come like this, why do we ask for security anyhow? Doesn't make any sense. Here's another example where you can switch between encrypted password or unencrypted password. I think it's a clever idea having unencrypted password because it's completely useless. But you see again what the thinking about those IoT service providers is. So and here's a thermometer with telnet configuration password. So why don't we get the defaults right? We're talking about this since 15 years. 15 years, we're buying those things and they come with the wrong defaults. Everything is open, lots of services, unencrypted channels by default, and default passwords are published all over the place. And the next question is, how can I integrate those devices into one single sign-on? How can I integrate it into one Active Directory and one LDAP? For commercial applications, for commercial SCADA systems, not that easy. And last but not least, and this is my first question to you, there's a small button somewhere where you can ask us questions, but I start off with a question. I'm looking for a multi-factor open source solution, which is running on the web platform, HTTPS, on Linux systems and on Windows systems, and is not a cloud-based solution. So a dual security is not my solution. I have one for single sign on Linux. I'm struggling for Windows. If you have one, I'm really interested in learning about those ones. Question and answer box is below, but en gros, control system cybersecurity still sucks. And then we got education. Here's a web page, a standard web page developed by one of the students at CERN. It's prone to cross-site scripting, so you can inject some code. Here's another one where you can make a directory transversal and you get more or less the local users that pass WD file on the Linux system. And here's another, the last system, which is a control system, which hasn't been patched for something like 11 months, and it was exploited by an attacker. So my wonder is, I'm hiring lots and lots of developers, software engineer, computer engineer, control system engineers, masters, bachelors, but on gros, they all come without security knowledge. And if you talk to them, they say, yeah, I got the database course, I got the operating system course, I got the C programming course, I got the course for web servers, but you know, security was just handled within 19 minutes at the very end. And I think this is bluntly wrong. Security shouldn't be something apart. Security should be something among all the others. So security should be part of maintainability, usability, functionality, availability. But for some reason, we are treating security still apart. So also there, control system cybersecurity sucks. So here's my last slide to explain to you why control system cybersecurity sucks and why it's a challenge for me and my colleagues to get this all best protected. First, the threats will not go away. There are attackers out of this world, nation states, script kiddies, hackers, activists, whatever else, cyber criminals who are trying to get into control systems because it's easy. They will not go away because it's something new fancy will come out of the market. It will just go worse. So the threats will increase in the future. You see in the complexity I'm running with the control system here at CERN, the vulnerability is always there. The vulnerabilities will not go away. This is a natural inherent part of software and hardware. We just should get our baseline better. We just need to get our baseline better protected from the vendor so they don't do blunder. They just come with something which is reasonably secured. But again, those vulnerabilities will increase, they will not go away. And if you look at the interaction between control system, nowadays we're living in symbiosis of control system. Just think of your home, how many control systems you have there, how dependent you are on electricity, on your heating, on your car, and on your cash machine. You will figure out we are all dependent on control system. And those dependencies, again, will not go away. So think of the consequences, everything will increase, and this is why control system cybersecurity sucks. Thank you very much.
Thank you very much, Stefan. We really appreciate that.
Yep, thanks everyone. If you do have questions for Stefan, please go ahead and ask them with the QA button at the bottom of the page. We do have Jerry Brower's suggested a link to some software there, and I'm going to post that in chat for everyone as a possible solution. So if you're interested, take a look at that later. We're going to move on to our second presenter today, Phil Salke. Phil is a computer scientist with over 35 years of experience in programmable controls, industrial automation, and embedded systems. He's presented ICS security training sessions at the NSF Cybersecurity Summit for large facilities and other cyber infrastructure conferences since 2015, and he was the keynote speaker for CACR's Cybersecurity Summit in 2017. Phil's software and hardware designs are serving sectors as diverse as food packaging, sewage processing, broadcast television, emergency power generation, lab and medical equipment, and nuclear power plant infrastructure. He is a managing partner of Generaia Industrial Automation, and since its founding in 2014, we're going to go ahead and turn things over to Phil. And don't forget to ask your questions at the bottom. Thanks.
Well, thank you. The biggest takeaway I think we can all get from what we've just heard is that no matter how complicated your system seems, there's a much more complicated one that somebody's got to take care of. The other side of that is, you know, we're all going to have job openings in our field about until the heat death of the universe. So we all have continued employment ahead. My side of the world is more of the industrial automation side, those programmable controllers you saw some photos of, hardened computer control hardware that's designed to remain in service for decades, never powered down, never rebooted. Security seen by the user there is nothing but a roadblock to making things work quickly and easily. The security issues are compounded by the timescales that are involved. There's plenty of running systems out there that were installed when Ethernet ran only on coaxial cable and twisted pair was something far in the future. Within the last week or so, we've seen malware that tries to target Windows-based supervisory control systems, SCADA systems, and a ransomware attack on a natural gas recompression plant. I've got systems that run in plants just like that one. That attack didn't target the ICS equipment, but it caused enough havoc with all the other data processing hardware that the operators were forced to shut the plant down. In both of those cases, our standard means of defending desktop systems would likely have been enough if they'd been properly applied. That being said, we'll look at the next layer down, protecting the existing control systems you have and that you may not even know that you have. And what I've got to offer you isn't a single device, it isn't a piece of software, it's a long, tedious, expensive process with no guarantee of success. But I haven't found a better way of approaching it yet. The first piece of it is a prerequisite before you even get to begin is inventory and discovery. It's an overlooked part of ICS security, but it's critical to doing the job properly. You'd never consider trying to protect an Ethernet network without having a pretty good idea of what address ranges it uses and what devices are supposed to be on it. But facilities all around the world have industrial control equipment and networks that aren't documented, they have no backups, they use multiple independent physical networking layers, and a bewildering variety of protocols. I recommend taking the time up front to do a complete survey of the industrial controls infrastructure in whatever facility you're trying to protect, if that's a single room in a lab or a whole university building. Document all the PLC and OIT components, all communication devices like Ethernet switches, serial protocol converters, modems, gateways, etc. It's a lot of walking around, a lot of looking in boxes. There's dozens of physical networking layers out there. There's hundreds of communication protocols, and there are literally thousands of equipment vendors. You're not going to be able to buy a single silver bullet box and install it to fix the problem. So you have to know what it is you're trying to protect. Next slide. Prerequisite 2, budgeting and triage. After you have a good solid idea of what you're trying to protect and what the potential attack surfaces might be, you're likely to find that there's more to do than you've got money or manpower. So looking at what each system does and how it communicates will allow you to decide which system to focus on first and how much time and attention it deserves. Is the system involved in life safety, like elevator controls or fire suppression? Is it mission critical for your business, like transgenic yeast fermentation? Is it important but not critical, like room lighting controllers or projection equipment? Or is it just decorative, like the controls for the fountains in the courtyard? Decide what you're going to protect in what order and how much of your limited time and money each system's going to get. And while you're preparing to ignore that fountain, remember that a casino got hacked through its network-connected fish tank heater. Next slide. Last prerequisite, documentation and backup, and I can't stress backup enough. Knowing that an ICS system exists and that it's connected to your network is not the same as knowing everything it's supposed to do, how it does it, and precisely how it talks to all the things it communicates with. Once you focus on protecting a given ICS system, you'll need to know not just what parts it has, but exactly what software it's running, what communication protocols it uses when it's talking to different devices, and which of those pathways are critical versus the ones that are optional or even unnecessary. Part of the process should be ensuring you've actually got copies of all the software and data. Data is often stored separately from the programs. Sometimes it's stored on different physical devices, such as production recipes that might be stored in a display screen rather than in the controller itself. Backing up an ICS system can require special integrated development environments, can need special vendor-specific cabling and adapters. Older systems may have specific requirements on the laptop you'll use, such as needing obsolete OS versions or native non-USB RS-232 ports. Well, now that we've gone through our prerequisites and we have some understanding of what we're looking at, what are our actions we can take? I've sorted these in order of sort of ease and cost. The first thing you can do, possibility 1 of 7, is to just ignore a system for now. Choosing not to work on a system at this time isn't the same as choosing not to do anything at all anywhere. Part of triage is deciding what's going to wait until later. You don't have infinite resources, so be prepared to say, hey, we're going to look at that courtyard fountain controller next year. Next slide. Possibility 2, monitor and protect, but don't interfere. You can install an interposing Ethernet switch and monitor its span port. That'll allow you to build alerts and help understand the traffic that's going on sufficiently to configure the rules for a later firewall installation. The good part of that problem is that industrial control system traffic tends to be limited in quantity, scope, and range. There's not vast amounts of data being sent around. Any one device is only using a small number of the possible ICS protocols, and it's generally only going to a few well-defined locations. So setting up alerts on traffic that is larger than usual, an unusual protocol, or is going outside the known hosts is straightforward and worthwhile. But first you have to figure out what those criteria are. Next slide. You can isolate a system. Now you may lose functionality, but what you're doing is you're ensuring that you can keep the core systems running. Sometimes you'll find a system has live communications capabilities that it doesn't use, doesn't need, or just too insecure to leave in place. I found DSL modems connected to remote systems. I've found Wi-Fi bridges that were installed on startup and were never removed. Vendor access tunnels left open in firewalls 24/7, 365. Telemetry ports for devices which were no longer in service but still provided external access to the controller. Or you may find a function that's in use because it's convenient. You know, the remote programming switch on a controller is left in remote mode because you might someday want to remotely program it, when you could switch it to run and now not have it able to be remotely accessed. You might find there's an internet-facing FTP port or a telnet port that you just can't in good conscience leave in place if there's any way around it. Now what that may mean is you literally have someone writing things down that used to get transferred automatically. That is probably not how you're going to leave it forever, but it may be the stopgap that lets you secure a system while you come up with another way to transfer the data. Next. Protocol-aware firewalling. Now, that's those magic boxes, right? There are now a few devices which are deeply aware of some of the more common industrial control system protocols, and they can firewall on the specific details of a given communication attempt. As an example, many controllers have a default access range for the Modbus, which is sort of a generic, the communication protocol that almost everybody talks. Their default access range is, well, anyone who signs on to me with no username or password, because there isn't any security in the protocol, can read and write all numeric and bit data in memory, but they can't change the controller program. Well, that's like saying that anybody who can attach to your computer can read or write any bit on the hard drive. You can put a thing called a Modbus firewall in place that can limit that data to only these 3 IP addresses are allowed to talk Modbus. They can only read those 7 specific data registers, and they're allowed to write 1 single bit device. Now, to install something like that, you require that complete knowledge of what will be transferred. Some devices are starting to come with what's called a learn then protect mode set. So you can put it in and it'll watch the data, figure out what's normal, and then stop anything that it hasn't seen before. However, if you don't know how to trigger every possible communication that that firewall might see, it's going to wind up blocking stuff that's going to be important later on. Protocol converters can be used in a firewall-like way for protocols that don't have specific firewalls available. You can take a protocol converter, read just the data you want from one given device, and then transfer it to a different port on that device, or even a different device, a different protocol converter, so that you now pick that data up and present it to the outside world as just only access to the specific things you want access to. So it's kind of it's a little more tough to build it, but you have much more control over how that's going to work. Next slide. Hardware and firmware updates. These, I'm just going to say, they rarely happen, and often with good reason. In industrial control circles, the idea of updating the firmware or the user software in a given system is usually frowned upon unless there's an overwhelming operational reason to do so. Control systems are often validated, sometimes by government agencies. They're proven to do the task they're programmed to do, and any modification of the underlying firmware or software is going to require a revalidation, time-consuming, expensive, and it involves downtime. To make matters worse, most of the known vulnerabilities we've found in industrial control systems are never fixed by the vendors. Some that are require replacement of hardware because the controller's firmware is not in flash memory, it's in masked programmed ROM. I kind of see that as a positive because nobody can get in and reflash anything malicious onto a programmable controller that doesn't have flash memory, but it sure makes the upgrades expensive. Next slide. Strategy 6 of 7, upgrade just the controllers. It's often worthwhile to leave most of a control panel in place. You'll find in a lot of instances, there's all kinds of extra hardware that's doing kind of electrical tasks, physical controls tasks, and the brain is one small part of that panel. So you can go in and find an older controller, an older human-machine interface, touchscreen, membrane key screens, pull those out, find something that's a pretty near form and fit replacement to what you pulled out. That makes the needed wiring changes easy. And now you might wind up adding a protocol converter to get from newer communications to the older devices that are still in the system. But now you can use those protocol converters as part of that firewalling we mentioned earlier. Again, to do this, you require a full understanding of the system's operation and all the communications pathways that are in use. You're going to need to be able to schedule downtime or have a temporary replacement system in place while the upgrade and testing is in progress. And then you're going to have to be able to completely recheck system operations once you're up and running with the new PLC and HMI. Finally, is you can replace the system. That's usually a last resort, but a lot of times it's a less expensive answer than trying to build ad hoc walls around extremely vulnerable older hardware and software. This path is only going to make sense. Again, you have to know everything about the system you're replacing, but you also have to take that opportunity to specify secure design in the replacement systems you order. Because you can be absolutely sure that if you don't specify robust security, you will receive a new system with absolutely no security. Those same default passwords, those same communication protocols that don't have any authentication, it's probably going to be much more vulnerable than the system you were replacing because it will be entirely reliant on Ethernet communications instead of things like twisted pair serial. And all the communications protocols that are going to be used by default are insecure without authentication. So that's my recommendation for a plan of attack. We start with discovery, understanding, and backup. Then we move forward with a well thought out action for each system we're trying to protect. For those of you who'd like to learn a little more, we've posted a link to an industrial control system security handout document I gave out at the NSF's Large Systems Cybersecurity Summit last year. It's got more details for planning and execution. It's got some sample specification language. It's got info on hardware vendors and notes on the Department of Homeland Security's ICS cybersecurity classes. One other thing I'm just going to mention IU has published a thing called the Information Security Practice Principles. It's a list of 7 sort of key words to keep in mind whenever you're dealing with security. Those words are comprehensivity. Am I seeing the whole field? Opportunity. Am I taking advantage of my environment? Rigor. What's the correct behavior and how do I ensure that it occurs? Minimization. Can I make this a smaller target? And in my world, that's very often, it's okay to say no. You want this to talk to that? Why do you want this to talk to that? We're not going to allow that. We're going to come up with a simpler way. Compartmentation. Is this made of distinct parts with limited interfaces? Fault tolerance. What happens if this thing fails? What's the fallback plan? And then proportionality. Is what I'm doing worth doing? Again, am I trying to protect the courtyard fountain? Information security practice principles. You can find links to that on IU's website. And that's it for me. Thank you.
Thank you, Phil. I have posted a link to those information security practice principles in the chat. To let everyone know, we had a couple questions. The slides and on-demand video will be available at researchsoc.edu/webinars. And with that, thanks to both of our presenters. And we do have a couple of minutes here for questions if you want to submit those through the Q&A box at the bottom of the panel. We'll take questions for about 1 minute here, and then we will sign off. If anyone has any questions, get them in now. Todd, do you have any housekeeping to take care of while we wait for questions?
We sure do. While you're waiting for questions, we would ask you to go ahead and look at the different ways you can connect with the Research SOC, our website, our announcement list, our blog, the community of practice, where if you don't, that I mentioned earlier at askcyberinfrastructure.org, there's a Research SOC specific area. And of course, you can follow us on Twitter. There are some events that we'd like to invite you to. Our next webinar on how to select and use operational cybersecurity metrics will be at 3 p.m. Eastern on March 19th. And then we'd appreciate it if you attend any of these conferences, the Internet 2 conference, EDUCAUSE SPC, where we will be a part of the IU table, and PERC, where we'll be there with our sister organization, Trusted CI. Stop by, visit, say hello. And of course, you can see all this information, as Josh mentioned, researchsoc.iu.edu/webinars. Phil's handout is available there now. The slides are available there now. And we should have the recording of this available in about 24 to 48 hours.
Sure. We'd have a couple of questions come in, which I replied to in text. We do have one for our panelists from Peter. What roles or SMEs do you recommend to bring together in doing this sort of work securing ICS for either panelist?
Stefan?
Let's get me in.
I'm gonna chime in a little bit as someone who comes in from outside of organizations a lot. What I tend to find is that a facility will often have a sort of a shadow IT department in the controls infrastructure that's living in the facility. They've set up their own networking. Vendors have their own networks inside boxes. They have their own connections to the outside world. They have their own connections to the house network that nobody even knows about. And while I'm a big fan of keeping control systems on their own networks just for operational reasons, you know, there's nothing like having the machine that's making all the money for you go down because somebody reprogrammed an Ethernet switch on the other side of a building that's in a locked cabinet somewhere. I like having control over everything. That's what controls are all about. But I want the IT department to really be totally aware of every IP address I'm using, even if it's not on their networks. I want them alerting so that if they see any traffic that's going to or from those addresses, they can page out to the entire universe saying something's wrong, we've been breached. So just getting people you've got available, like folks from your IT department involved in the controls networking, people who've got that security background, it's all going to help.
Yeah, may I add to this one? We got one comment of somebody who said only solidified my frustration. Apologies for this one. Of course, there are solutions. The first thing is cybersecurity, control system cybersecurity or others depend very much on inventories. If you know what you got on the network, if you know which operating systems you're running, what the patch status is or the no patch status is, if you know who the owners are, which libraries are installed, which access rights they need, how they talk to each other, those inventories which you can already start building up. I'm not saying you should go for the most complicated ones, but for me, knowing which web pages we have, knowing which devices on the network, which accounts I have, which virtual machines I have, this is already the start. The next thing is what Phil already said is, don't reinvent the wheel. You got, I hope like we got, you got an IT department with professionals in networking, in databases, in operating systems, in hardware, in virtualization, and in web servers. So what we did is we brought those communities together. We get control system experts, which are brilliant at what they're doing, control systems, but the networking, their network for the control systems done by the IT department, the networking group. We have one group which is doing networking for CERN. Office computing, internet connections, wireless, telephony, but also control system networks. One team, one network group. Databases, same thing. This is not the core competence of control system engineers. So don't let them do it. Give them the chance to get a database from your IT department. We have database group, which is doing finance and HR application databases, industrial database for control systems, but also databases for the average users, and so on. So you bring those sides together. We get one security team. I'm doing security for office computing, infected laptops and all those weirdy things. I'm doing computer center security, so what's running our computer center, and we're doing control system security together. So this is, again, one group. So just jump over the fence and bring the OT, the control system people, and the IT people together. And with this, you can already start generating a much, much higher security stance. Last but not least, I have the luxury position, I control CERN's firewall, which means that every single opening in this firewall needs to be authorized. The device behind needs to be penetration tested, and I got life cycle. And we're automatically closing openings which are not used for a certain time, which means that no telnet, no FTP, no SSH, nothing which is deemed by me and my team as critical for operations.
Thank you. We have one more question, just 3 or 4 minutes here. Are you seeing any traction on standards like the ISA IEC 62443-4 in the industry, and if so, which ones? What are the implications regarding selection and cost? Do either of you would like to address that? I'm not familiar with those standards myself.
I can take the undiplomatic, direct, and frank stance, and I'm pretty sure Phil can then take the real stance. For me, pick one, doesn't matter. SP99, ISO standard, ISA standard, they're NIST standards. Every sector energy has their own standards. It doesn't matter for me. I have a room full of standards. Just pick one, follow this standard, and once you're through with this, take another one for verification. If you've done that part and you're at that level that you're compliant with whatever standard you've picked for control system, well done. Pick a second one for verification, and then you can show me how you've done it.
And what I'm seeing out in the real, there's a very high level where things like these standards occur, and then there's feet on the ground. And if nobody's specified that things are going to be built to those standards, all those things do is they get in the way of people getting their work done. And the various people who are designing systems look at all this stuff and just say, I can do something that's going to require me to learn all these things about security, or I can not do those. Well, if nobody's forcing me to do it, I'm not going to do it. So we're seeing just the very start of even things that we would consider trivial, like protocols with robust authentication mechanisms. Well, that's not trivial when you're running it on tiny, tiny hardware that these control systems tend to have. So, then the other thing is we don't have a standard implementation of these things. So everybody's rolling their own security, and everybody's coming up with some partial implementation of a standard that's got gaping holes in it one way and another, and things that don't work. I mean, I've found stuff like Ethernet controllers that don't respect the port structure. So you can put in a programmable controller, and instead of talking to it on a given port, any port you talk to it on, it'll answer Modbus from any port you like. How do you even firewall something like that? And if somebody's going to design something like that, you hand them a security standard and say, we need you to build your stuff that works to this standard, the chances of them doing it are pretty low. So I'd love to see it happen. I'd love to see it get a lot more traction, but unless it's an area where someone's really paying attention and specifying this stuff, maybe in the higher ends of pharmaceutical, we're just not seeing it.
Thank you very much. Thank you, Phil. Thank you, Stefan. Ladies and gentlemen, we're just about out of time. One correction to that, to the previous slide. Our next webinar is the 20th of March.
It is the 19th, but it's it's EDT, not EST.
Right, EDT, not EST on Thursday. And that's about all the time we have. We thank you very much for attending. We thank our guests for their great presentations. Again, we thank everybody for your patience as we work through technical glitches, and we hope to see you at our events and next webinar. This concludes our webinar for the day.